One of the difficulties of chemistry is going back and forth between multiple representations of the same molecule and trying to infer from these representations the properties of the molecule. Let's look at this example. These yellows should be color-coded gray. They represent the molecule butane, in which we have 4 carbons. Now, I've drawn it in this particular conformation in which the dihedral angle, or torsional angle, is 0 degrees. In other words, looking down this carbon-carbon bond, these bonds coming off of the 2 carbons are all eclipsed. So this has a basically dihedral torsion angle of 0. Now we can also represent it obviously in this diagram, in this sort of line drawing diagram, as just these lines. And then of course there's the Newman projection as this, in which now this carbon right here is this carbon right here. We're looking down this axis. We have a back carbon and a front carbon. Coming off the front carbon right here would be a CH3 pointing upward. That's this group right here. Coming off the back carbon, which is this outer circle, is this CH3 group pointing upward from the back circle. So I think you can tell from this diagram and also from this diagram that if we sight down that carbon-carbon bond, I have 3 pairs of bonds that are eclipsed. The carbon-hydrogen bonds are eclipsed, and then the bonds to the methyl groups. And that can actually maybe better be seen from the Newman projection, in which I have eclipsed bonds here, and eclipsed bonds here. Each torsional strain through these bond-bond interactions counts 1 kcal per mole, so that gives us so far 3 kcal per mole destabilization of this molecule in this particular conformation. Now, if we look at this molecule, there's an additional kind of strain called the steric strain, and that's due to atom-atom interaction. And I think if I rotate this molecule, I think you can see that these atoms are butting up against each other fairly closely, and these are hydrogens. So if I were to just call that hydrogen 1 and count backward to try to get to this hydrogen, that would be atom 1, 2, 3, 4, 5, 6. This is an example of a 6-atom interaction, a steric interaction that contributes an additional 1 kcal per mole to the strain in this molecule. Couple that with the 3 kcals per mole through the torsional interactions, the total destabilization of this molecule, when the dihedral angle is 0, all the bonds are eclipsed, is 4 kcals per mole. Now I'm going to rotate along this torsional bond, this bond right here, 60 degrees, and I'm going to see what happens to both this ball and stick model and to the Newman projection. So here we go. Okay, we rotated 60 degrees, and notice when we did so, this skeletal stick diagram, line diagram didn't really change. But now if I rotate this molecule back here, and I think you can see, now we're sighting down this carbon-carbon bond. I think you can change now. We've basically created a conformation in which this is 60 degrees. This is a Gauss conformation. Likewise, you can see from the Newman projection, the back CH3 is rotated to the back, but notice that there's still interactions here. However, we've completely eliminated the torsional strain because these bonds are no longer eclipsed. So the net torsional strain here is 0, but I still have interactions here, 1 6-atom interactions. And I think you can see that if we count back. And if these were rotated toward each other optimally, we see 1, 2, 3, 4, 5, 6. And again, that would require a little rotation around this bond to show that these would butt up against each other. So we can still count that as a 1,6 interaction. So the net destabilization now is only 1 kcal because we've gotten rid of these eclipsed interactions when we have this Gauss conformation. Now let's rotate to a 120 degree bond angle and see what happens. Okay, now this bond angle is 120. Again, I'm sighting down the carbon-carbon bond. And you can see now the back carbon is rotated 120 degrees. And you can see again the bonds are all eclipsed. That sort of is also reflected in this now newly sort of bent version of the skeletal diagram, but best seen in the Newman projection, in which the back methyl group is now here. And we can clearly see the 3 sets of bonds that are interacting through torsional interactions contributing 3 kcals per mole. But notice the 2 CH3s are far enough apart, there is no longer any 1 6-atom interactions. So, if I count backwards, these are too far apart. They're facing in opposite directions. So, at this point, we say there are no 1 6-atom interactions. When the CH3 was up here and the torsional angle was 0, they were very close to each other. when they were Gaussian, we still say they were close together, but 120 degrees apart. They're so far apart, pointing in opposite direction, that there's no steric interaction. So the net destabilization here is just due to the 3 overlapping pairs of bonds, torsional interactions, or 3 kcals per mole. Finally, looks like at the 180 degree torsional interaction. And again, if I were to rotate this molecule over here, again, we're sighting down the carbon-carbon bond. This is the front carbon right here, and there's a CH3 group pointing up as indicated in red here. And going back, coming off the back carbon, there's a CH3. Now it's going down. And I think you can see that all the bonds are no longer eclipsed. These are anti from each other. The methyl groups are on the opposite side of this carbon. And so none of the bonds are eclipsed, so there's 0 torsional interactions here. Also, if you look at the methyl groups in the Newman diagram, they're as far apart from each other as possible. So there's no steric interactions as well. So this is the most stable conformation in which there is no steric interactions or no torsional interactions. And if literally I was to count the distance in terms of atom number from this H here on the methyl just to one of these adjacent H's, I'd go 1, 2, 3, 4, 5. So these are 5 atom interactions. So then you can tell that from here, if we count one of the H's as 1, then we go here 2, then we go here 3 to the front carbon, then we go to the back carbon circle 4, then one of the H's 5. Again, 1, 5 interactions don't contribute anything to steric interactions. So the trick here is to be able to go back and forth between multiple representations of the molecule, whether it's ball and stick, a line drawing, or Newman projection. And look at the this projection right now, not this projection, but the line drawing. You can see that it's got the characteristic zigzag pattern, and that's because if I were to actually rotate this molecule, you can see the characteristic zigzag, in which looking down this bond, the methyl groups are on basically anti to each other, minimizing steric and torsional interactions, and that's why we represent them in their lowest energy conformation with this zigzag diagram.